Something you should know from before is that the gradient at a single point on a curve is equal to the gradient of the tangent to the curve at that point. This section relates to how you can go about determining the equation of this tangent through a bunch of simple steps. To determine the equation of a tangent to a curve at any point, carry out the following three steps. First, you find the derivative of the function representing the curve. Then substitute the x-coordinate value of the point at which you need to determine the tangent equation to calculate the gradient of the tangent. And finally, using y equals to mx plus c, the x and y coordinates of the point and the gradient value determined, just rearrange and solve for the y-intercept c. Then you'll have the equation. Here's an example. Find the equation of the tangent to the graph of y equals to x to the power 4 plus 1, 5 x squared minus 3 at x equals to 0, 5. Then going step by step, step 1, determine the derivative, which you'll get as 4x cubed plus 3x. By the way, from here on out, I'll assume you're pretty comfortable with doing differentiation using the various rules, so I won't go through all the steps and I'll just write the final derivative equation. If you're still not fully on top of it, it's a good idea to pause just after I write the derivative, then try to do the differentiation by yourself and see if you can get the same answer. Then resume. So that was step 1. Then step 2, you just sub in the x value to get the actual gradient, giving you the gradient as a value of 2. Lastly, step 3, where you use y equals to mx plus c, and just sub in the values and rearrange for c to get the final piece of the puzzle. But this time, we only have the value of x and m, but not y, because they didn't give the full coordinates. No stress, just calculate it using the function equation by subbing in the x value of 0, 5, which gives y as minus 2, 5625, or in the quicker to write fraction form, negative 41 over 16. Now we have everything to solve for c. Sub in the values and you will get c as negative 3, 5625, or negative 57 over 16. And just sub in the gradient m and c values to y equals to mx plus c, and you finally get the tangent equation as 2x minus 57 over 16. Then for the last bit of info related to tangent equations is something known as the normal. Put simply, the normal to a curve at a particular point is the line perpendicular to the tangent, meaning at a 90-degree angle to it. And the product of the tangent's gradient and the normal's gradient equals to negative 1. And you can use this info to determine the equation of the normal. Here's an example. What's the equation of the normal to the graph of y equals to x to the power 4 plus 1, 5 x squared minus 3 at x equals to 0, 5? This is the exact same function as the previous example, so we already know the tangent's gradient, which was 2. Using the equation I just showed and rearranging to make gradient of normal as the subject, and subbing in the tangent's gradient value gives the gradient as minus 0, 5. You now have its gradient, and from the previous part we already know the full coordinates of the point. Then just sub these in to y equals to mx plus c, solve for c, and you'll finally get the equation as y equals to negative 0, 5x minus 37 over 16. Let's move on to the next topic, which is second derivatives. The second derivative sounds pretty hectic, but it's not so complicated. The equations we've been getting so far when differentiating a function is known as the first derivative. The second derivative is just the equation you get when you differentiate the first derivative. And what it represents is the changes in the gradient of the original function. This makes sense, right? Since the first derivative represents the gradient, which is a measure of how a graph's y value changes with changes in its x value, the derivative of this will indicate how the gradient changes with changes in the x value. Before I show this in an example, I need to introduce some new notation needed to describe the second derivative. As a reminder, the first derivative is written using f prime x, y prime, and dy over dx. Then the second derivative is pretty much the same notations with a little extra portion. The f prime x form for the second derivative is this term, which you can say as f prime prime or f double prime x. Then the dy over dx form becomes d squared y over dx squared. This one is a little funky. Don't worry about why the d is squared in the numerator and the x is squared in the denominator. It's just how someone decided to name the term. So when you see this, don't think of something being squared. It just represents the second derivative. And lastly, y prime just becomes y double prime. Here's an example. Determine the second derivative of the following functions. Part A is fx equals to 3x cubed minus 9x squared plus 4x plus 20. So they gave us fx. Then differentiate it to give f prime x. Then differentiate it again to f double prime x, using the exact same rules we covered before for the first derivative. There's no special new rules for the second derivative. When you differentiate this, you'll get 18x minus 18. And you're done. As simple as that. For part B, you need to get the second derivative of L as a function of x equals to 6 over root x plus 400 times x to the power of 50. So L of x is, then L prime x would be negative 3 times x to the power of negative 1, 5 plus 20,000 times x to the power of 49. And finally, L double prime x is 4, 5 times x to the power of minus 2, 5 plus 980,000 times x to the power of 48. You can just take the negative exponent term down to give the second derivative as 4.5 over x to the power 2.5 plus 980,000 times x to the power of 48. And that's all there is to know about determining the second derivative. That's relatively simple. But the way the second derivative is applied, on the other hand, is a little tricky. And that's related to the sketching of graphs. This was the part I remember having the most difficulty trying to understand when covering this material for the first time in high school. But thankfully, now all these years later, I understand it pretty well and have developed the simplest tactics I could to help you make sense of it. Let's move on to the next section of the topic, graph sketching. So you've already learned how to sketch quadratic functions in previous years. What's new in grade 12 is now you need to learn how to sketch functions that are cubic polynomials of the form ax cubed plus bx squared plus cx plus d. First thing to know is that these functions will have two turning points, and the value of a in the function affects how the shape of the graph will look. The first situation is for a values greater than 0, whose graph will look like the following. The best way I could think of to remember this shape is as a mountain followed by a ditch. It's a little funny, but it's probably the easiest way to remember the shape. Then the second situation is for a values less than 0. And this time the shape would be the opposite, a ditch followed by a mountain. Then what about for a values equal to 0? Well, nothing. The x cubed term would cancel off, and these would just be quadratic functions, which you already know how to sketch. The next part under graph sketching is concavity. Concavity is a term used to describe the way a curve's gradient changes as you move along it. Before I dive deeper into this, I first need to describe something related to the way a curve's gradient value can vary. This is an important diagram, and what it represents is the tangent of a graph at any point and how it can change based on how the tangent appears, going from a lower x value to a higher x value. Think of these blue lines as being the x and y axes, and this red line is the tangent to a graph at some point along it. So if the tangent to the curve is horizontal, its gradient will be 0. then if it's facing upwards, it will have a positive gradient value. Then as it becomes steeper and steeper, the value increases. And eventually, when it becomes vertical, the gradient becomes infinity. The gradient of any vertical line will always be some positive number over 0, which is undefined but basically like infinity. Then if the line is facing downwards, it will have a negative gradient value, which becomes more and more negative till it eventually has a value of negative something over 0, which is undefined but basically like negative infinity. Just keep this diagram in mind because we'll use it slightly later on. Then coming back to the situation where the tangent is a horizontal line, notice that for a curve, the only places where the tangent is horizontal will be at the turning points. In calculus language, turning points are points where the tangent to a graph has a value of 0 are known as stationary points. And that's because at a turning point, the function neither increases nor decreases. It's just stationary. For any function you're given, the gradient is determined by differentiating to get the first derivative. Therefore, at the stationary point, the first derivative is equal to 0. By doing this, you can solve to get the x-coordinates of the turning points, then just sub those into the original function to get the y-coordinates. So say if you're in a situation where you're given some function and just had a minute to make a rough sketch of it, just by determining the stationary point coordinates, you'd have enough info to make such a sketch. But for an exam level question, you need to make a nice smooth graph, for which you need to determine the intercepts as well. Therefore, to sketch a smooth graph of a cubic function, use the following steps. First, you'd deduce the general shape by looking at the a value, meaning the coefficient of the x cubed term. The general shape refers to the whole mountain and ditch shapes I earlier mentioned. Second, you determine both intercepts, first the y-intercept by setting x equals 0, and then the x-intercept by setting y equals 0, at which point you need to use factor theorem and similar techniques I covered in the polynomials video to get the different x-intercepts. Then third, you would solve f prime x equals 0 to get all x coordinates of the turning points, then sub these into the original function to get the y values. And you now have enough to sketch the curve. And just do the final step now, which is plotting all the points just determined and joining them together to get a smooth curve. Let's look at an example. Sketch the function hx equals to x cubed minus 2x squared minus 5x plus 6. Starting with step 1, you compare it to the general form of a cubic polynomial and see what the value of a is. In this case, it would be 1, which is more than 0. Therefore, it's a shape with a mountain followed by a ditch. Next, you determine the intercepts starting with the y-intercept by subbing in x equals 0 to get a value of 6. So the y-intercept is 0 and 6. Then solve for the x-intercept by setting y as 0, which gives the equation. Then you have to pull out the tricks to solve for cubic polynomials. The first is trial and error. Starting with an x value of 1, sub this into the original function, which would equal to 0. Therefore, x minus 1 is a factor. Next step is inspection, which gives x minus 1 times x squared minus x minus 6. And this quadratic equation factorizes to x plus 2 times x minus 3. Then you just equate these to 0 and rearrange for x to solve for the x-intercepts. And the three intercept values you get are 1 and 0, 3 and 0, and negative 2 and 0. Then you go for step 3, where you'd equate the derivative to 0 to get the turning points. First, the derivative is h prime x equals 3x squared minus 4x minus 5. Then equate it to 0 and solve for x. Unfortunately, this quadratic equation turns out to be one that can't be easily solved just by inspection. So you need to use the quadratic formula. And if you do that, you get x as 2 plus root 19 over 3 and 2 minus root 19 over 3, which to two decimal places are 2,12 and negative 0,79. Then when you sub these back into the original function, you get y as negative 4,06 and 8,21. Therefore, the turning points are 2,12 and minus 4,06 and negative 0,79 and 8,21. We now have enough info to plot the graph, and this will look like where all the key points you'd use to plot it are shown in black. Cool. So whenever given a cubic function and asked to sketch it, you just follow the same bunch of steps. Now remember that this section was titled concavity, and I had said that's related to how the curve's gradient changes as you move along it. Now we'll actually use the word concave to describe graphs. There's two alternatives. First is concave up, whose graph would look roughly like one of these two shapes. Then there's concave down, which would look like one of the following two. You don't need to memorize all these funny different shapes. I'll describe how to distinguish between concave up and concave down soon. So when I personally was trying to learn which shape is concave up and which is concave down, I thought it may relate to the usage of the word concave. The only place I'd heard the word before was in relation to lenses. You may have heard of concave and convex lenses. This is what a concave lens looks like. I personally couldn't find any easy way to link those different shapes to the shape of the lens. So I honestly don't understand why it's described using the word concave. So I suggest don't try to think of it in relation to a concave lens. It's just some funny mathematical terminology that someone decided on at some point. I will teach you a method to deduce on the spot what shape it is, and this uses the gradient diagram that I showed you earlier on. First, some important terminology that you absolutely need to understand, and that is the difference between concave up and concave down. Concave up means that for the graph, the gradient increases as x increases. And concave down means that the gradient decreases as x increases. Here's an example demonstrating the method to determine whether a graph is concave up or concave down. Say this is the graph you're given, and you need to determine whether it's concave up or concave down. The strategy is to determine whether the gradient increases or decreases as x increases. What as x increases means is as you go to the right. So you start by drawing the gradient diagram at the beginning of the graph. Then note what the gradient value approximately is. Firstly, at the start, the graph is in the upwards direction, so the gradient is positive, and it's somewhere between 0 and infinity, so you can say it's moderately positive. Then draw the gradient diagram at the end of the graph, so on the rightmost portion of it. The end of the graph is also in the positive direction, but this time it's much closer to the infinity end of the diagram, so it's a high positive value. The gradient goes from a moderate positive value to a high positive value, meaning it increases as x increases. Therefore, it's concave up. Then the last thing is to see how the y value changes as x increases. In this case, y increases as x increases. Therefore, it's an increasing function. Therefore, the full description of the graph shape is concave up increasing. Let's look at another example. This is the graph this time. So follow the same procedure. First draw the gradient diagram at the beginning of the graph. This time the graph starts off in the downwards direction, so the gradient is negative, and it lies somewhere in between 0 and negative infinity. So we can say it's moderately negative. Then do the same at the end of the graph. This end is also in the negative direction, but much closer to the negative infinity part of the diagram. So we can say it's a very negative value. Therefore, the gradient goes from a moderately negative value to a very negative value. To put this in numbers, from something like -10 to something like -200. Therefore, the gradient decreases as x increases, so it's concave down. And lastly, the y value decreases as x increases, so it's a decreasing function. Hence, the full description of the shape is concave down, decreasing. So that's the visual way of determining concavity. Then there's also the more analytical or mathematical way of determining it, and that's using the second derivative. How it works is, if at a certain x value the second derivative is more than 0, then the graph is concave up. If the second derivative is less than 0, then it's concave down. Then there's a third case where the second derivative is equal to 0. And what that means is that the concavity is changing, and this is known as a point of inflection. Let's apply it to a basic example. The function is gx equals to x cubed, whose first derivative would be 3x squared, and whose second derivative would be 6x. Looking at the second derivative, we can see how it would behave for different values of x. For x values greater than 0, the second derivative would also be greater than 0, so concave up. For x values less than 0, the second derivative is also less than 0, so concave down. And for x equals to 0, the derivative is also equal to 0. So at x equals to 0, there's a change in concavity, so a point of inflection. Now for the final part of the graph sketching section of the topic, let's look at an example tying together both the visual and the mathematical ways of assessing concavity, which will hopefully help it all make sense. I'll use the example from before for which we already have the graph. The function was h of x equals to x cubed minus 2x squared minus 5x plus 6. And its first derivative would be 3x squared minus 4x minus 5, and the second derivative 6x minus 4. So as earlier defined, a graph is concave up when the second derivative is more than 0. So when 6x minus 4 is more than 0 for this function, meaning when x is more than 2 over 3. Then we know that it's concave down when the second derivative is less than 0. So when x is less than 2 over 3. And lastly, there's a point of inflection when the second derivative is equal to 0, so when x equals to 2 over 3. If you sub this into the original function, you get y as roughly 2,07, giving the point of inflection coordinates as 2 over 3 and 2,07. Let's look at how this plays out in the graph. This was a graph we'd gotten, and if you plot the point of inflection, it looks like. But this is quite messy and kind of an eyesore, to be honest. Let me remove a lot of these black points and coordinates, because they aren't needed. That's much better. Notice that the point of inflection is exactly between the two turning points. Let's see whether the concavity actually changes at the point of inflection. To assess the change in concavity, we need to look at the shape of the graph before and after the point of inflection. So the graph changes from this sort of shape to this sort of shape. So from this to that. Then let's determine the concavity of these two curves, which you do by placing the gradient diagram at the start and end of both of them. This is how it looks for the first curve. And this curve goes from a moderately negative value to a very negative value, meaning a decrease in gradient. So it's concave down. Then for the other curve, the gradient goes from very negative to moderately negative, meaning it increases in value. Therefore, it's concave up. That means at the point of inflection, the concavity does change from concave down to concave up. Then we can also test the other conclusions we reached. One was that it's concave down when x is less than 2 over 3, so to the left of the point of inflection. I'll go back to the original diagram so we can see what sort of curves were there. So for x values less than 2 over 3, to the left of the point of inflection, you had it going from this sort of a curve to this sort of a curve. So like this. So we need to determine the concavity of these two different curves to see if they're both concave down. And we've already determined that this curve is concave down in the previous part. So just have to assess this one and check whether it's also concave down. Like before, you just place the trusted gradient diagram at the beginning and the end of the curve. The curve goes from very positive to moderate positive, so a drop in gradient. Therefore, it's also concave down. The other conclusion was that it's concave up when x is more than 2 over 3. Let's see what sort of curves are there after x equals to 2 over 3. So after 2 over 3, meaning after the point of inflection, the curve goes from this sort of a shape to this sort of a shape. So something like that. Earlier on, we already confirmed that this one is concave up. So just have to do the assessment for this other curve. And we find that this one goes from a moderate positive to a very positive gradient. So the gradient increases, meaning it's also concave up. Therefore, this conclusion also checks out. And that's everything related to sketching graphs and concavity. That was the hardest part of the differential calculus topic. So the worst is now over. We're just left with the final section of the topic, which is related to applications of differential calculus. Before that, you just need to learn one last sort of terminology related to graphs, specifically those of cubic functions. So for a graph that looks like this, which is a valid example of a conventional cubic function, notice there's a maximum and a minimum turning point. But these turning points would actually be called a local maxima and a local minima. And they now have this extra word local before them because they no longer represent the absolute maximum and absolute minimum values of the curve. There's other points with y values higher than the value of the maximum on the right side as the curve continues with increasing x values. Then there's also points on the curve with y values lower than the value at the local minima point on the left side of the curve as you keep decreasing the x value. So they don't represent the actual maximum and minimum values of the function, they're just a maximum and minimum in this local region of the graph. Now moving on to the final section, applications.